So the periodic table. Dmitri Mendeleev often gets credit for being the originator of the modern periodic table. So in 1869, he was a Russian chemistry professor. He noticed that certain groups of elements had similar properties. At this point, they had discovered many different elements, but there was no way to organize them. It was just random. I guess you could alphabetize them or something, but it was pretty random. We didn't have a table like this. So he's looking for patterns, and he found that if you listed the elements in order of increasing mass, there were properties that reoccurred periodically. And this gives us what's called the periodic law. When the elements are arranged in order of increasing mass, certain sets of properties recur periodically. That's why it's called the periodic table. So it's a little bit like a piano keyboard, where you have middle C, and then you go up an octave, and there's another C, which is like it, but it's just higher, right? It's a higher harmonic, and then you go up again, and there are these patterns. So here we have hydrogen, and we go up 8. Strange that it's 8, just like an octave. And here's another element that has some similar properties. And then we go up here, and there's another element that has similar properties. And so the green one's here, and the blue. So this is the periodic nature of the table here. So you put them on this long list, and you see these recurring properties. And so he said, well, what if we, instead of making this long list, which is really too long for a piece of paper, if nothing else, what if we wrap this around and make it into a table, and we'll stack up all the elements that have similar properties? So just looking at the first 20 elements in a very simple form, we stack them up, and we've got these blue ones lined up on top of each other, and the purple ones, and orange, I guess that is, and green. Hydrogen's sitting over there. I'll talk about him later. So he did with this with the elements, and when he put this together, there were some gaps, some missing pieces. And so he predicted that elements would be found to fill in those holes. And he even predicted the properties of those elements. And sure enough, they were discovered, and their properties were remarkably similar. This is just kind of an interesting periodic table. It gives broad ranges of when these things were discovered. And so we see that, these guys down here have all been discovered or created since 1950. And some of them have been known since before 1800, these lighter blue ones. So in 1869, not all of the elements had been discovered. And this is how in 1869 Dmitri Mendeleev completed the first periodic table. So in the modern periodic table, the elements are listed not in order of increasing mass, but in order of increasing atomic number, the number of protons. And we have more elements than the original table because more have been discovered. What am I supposed to say about this? There's a lot of information in the periodic table, and the longer you study chemistry, you realize, wow, there's just so much more information in here than I even realized. So we'll just start with the basics here. Most periodic tables have this dark line here. I call it the stair-step line. The periodic table on the wall didn't have one, so we took some blue tape and we made it because we like the line. That line divides the nonmetals from the metals. So over in this area we have the metal elements, and up here we have the nonmetals. And then the ones that are right along the line are called semi-metals or metalloids. In the table, they're between nonmetals and metals, and in properties and characteristics, they're between nonmetals and metals. We have these guys down here that are sort of taken out. Due to just the geometry of our classroom and the board and everything, the periodic table on the wall is actually how it was intended to be displayed. But it's very long and narrow, and so it doesn't fit on a 8.5 by 11 piece of paper very well. So this is how we usually see it. But what we should do is take a pair of scissors and cut it right here and put these guys in. And so if you look at the atomic numbers, we've got 55, 56, 57, and then it jumps to 72. No, you have to go down here. 58 through 71 are down here, and then you can come back up here. These are pulled out because, well, it doesn't fit on a piece of paper, and those are rather uncommon elements. We don't use them very much, and so we just pulled them out. These are called the lanthanides because they come after the element lanthanum, and these are the actinides because they come after actinium. So characteristics of metals, nonmetals, and metalloids. Metals are good conductors of heat and electricity. Nonmetals pretty much have opposite characteristics, so they are poor conductors of heat and electricity. Metals are malleable and ductile, meaning you can hammer them into a sheet or draw them into a wire. Nonmetals are not. A lot of nonmetals, if you hit them with a hammer, they'll shatter or break. They're not going to smush like metals do. And for chemistry, the most important thing here is that metals tend to lose electrons in chemical changes, and nonmetals tend to gain electrons. The metalloids are in between. They're sometimes called semimetals or semiconductors because they do conduct electricity, but a little bit, not as well as metals. We can also look at other divisions in the periodic table. Here in yellow, these two columns kind of stick up over here, and these columns stick up higher. These guys sank down. So they even colored this blue, which makes me think of this as being like a river or something, and these are the two banks. They're sandy colored, right? So these are the main group elements, and these are the transition elements. So transition from one of the main groups to over here to the other main group. And then we have some group numbers. A group in the periodic table is a column, and so we numbered them. There's two sets of numbers here. Just regular 1 through 18, and that's what IUPAC says we should use, the International Union of Pure and Applied Chemistry. And then because Americans just like to be different, we have the current U.S. usage group number. So that's the 1A, 2A, 3A. So the main group elements all have group numbers that end with A, and the transition elements have group numbers that end with B. I really don't have much use for those numbers, but the main group element numbers are pretty useful. So columns are groups and rows are periods. And so we also number those. So we've got periods 1 through 7. And there you go. So we should be able to identify whether something is a main group or a transition element, and what period and group it's in. Some of these groups have special names, and these are ones that you should know. The noble gases are group 8A. They are generally very unreactive. The alkali metals are group 1A. They are all very reactive metals. Alkaline earth metals are next to them in group 2A. They are not quite as reactive. And then the halogens are group 7A, and those are very reactive nonmetals. So metals tend to lose electrons, and they form cations. And the main group metals, many of them form predictable ions. They lose a predictable number of electrons. So for main group elements that form cations with predictable charge, the charge is equal to the group number. So that's the current U.S. usage group number, the one with the A on it. And on this periodic table, it didn't originally have those numbers, and we stuck them on there because we like them. The main group, nonmetals, tend to gain electrons, so they form anions, negative electrons. There's a couple of different ways to think about or to be able to predict what the charge is on these nonmetals. They're going to form anions with the same number of electrons as the nearest noble gas. That's one way to think about it. They form anions where the charge is equal to the group number minus 8. So if it's in group 7, 7 minus 8 is negative 1. Or when we get to a picture, I'll show you, you can also look at it like a game board and you're counting backwards. The transition elements have lots of different ions. They tend to be squirrely and unpredictable. So we'll see group 1 tend to form +1 ions, group 2 form +2 ions. The halogens form -1, and the oxygen family, I don't know why that guy never got a real good name, tends to gain 2 electrons. Okay, this is better. Sometimes pictures are much better than words. So over here we have group 1. These guys all form +1 ions. Group 2, +2 ions. Group 3, +3 ion. So those aren't too hard. The nonmetals. So over here in group 7, these all form a -1. So again, the group number -8, that works. But you can also think of this, it kind of looks like a board game, right? And if this is your starting point, you're moving backwards, -1, -2, -3. And that's what I find students like the best, is just count backwards from the noble gases. 0, -1, -2, -3. So we can predict the charges of these elements just by their position on the periodic table. So let's practice. Predict the charge of the monoatomic ion formed by nitrogen. Well, find it on the periodic table. There it is right here. Is it a metal or a nonmetal? It's a nonmetal. Nonmetals make negative ions. So if we start over here, the noble gases don't make ions. So these guys are 0, -1, -2, -3. So nitrogen forms an ion with a -3 charge. So predict the charge. The charge is -3. And if we're going to write the symbol for that ion, it's N3-. How about rubidium? What charge would a rubidium ion have? +1. So we find in the periodic table, it's down here, metal or non-metal. Well, it's a metal, right? So metals form positive ions, and it's in group 1A. So it's going to form a +1 ion. So the charge will be +1, and if we want to write the symbol for that ion, it's Rb with a +1, just a positive sign. Any questions?